Now we'll have a look at some more experimental design terminology. I did say we weren't going to look at too much more in this topic, but I may have lied. We are going to look at a little bit more, but not too much. We're going to look at concepts such as balance, placebo, which should be a term that's familiar to you, and double-blind trial. Balance is an easy term to come to grips with. It simply means that there's the same number of individuals allocated to each of the treatments being applied in that experiment. So in the feed type example, where we had feed A and feed B, there were 40 farms allocated to feed A and 40 to feed B. So 40 in both, that means it's balanced. Balance makes stats a little easier. It certainly makes it more consistent, but it's not 100% necessary. It's not compulsory. And most experiments end up not being balanced due to losing an experimental unit, just not finding enough. It might have an odd number of experimental units, and so inevitably one has to have less than the other. We move from balance, a simple concept, to experimental error, which is equally as simple, really. But it is an incorrectly used term. Often error is used in place of standard deviation, where that's not necessarily correct. Here we refer to experimental error as the variation we see which isn't due to a treatment, a particular treatment. So if we have two individuals, both of which receive the same treatment, but we get a different result, that is experimental error. So we have exactly the same environmental conditions, but the result is different. That can be due to a number of different reasons. Often it's genetic differences between the experimental units that we're using, so the plants may have slightly different genes, different humans obviously have different genes. It may be due to actual errors made in the measurements, so human error. It may be due to slight environmental differences which were occurring at the time of measurement. It may be the device itself, so not the experimenter but the actual device being used, which actually has a bias or some sort of error within it. During the inferential statistics component of this subject, we'll be seeing how we can calculate the magnitude of this error. A classic example of experimental error in a wine tasting sense is when the same person tastes the same wine twice and gives that wine a different score. That would be experimental error. We try and minimise the size of experimental error wherever possible. First of all, we try and minimise the experimental error due to ourselves, so recording the wrong number down or using an apparatus incorrectly. We calibrate our measurement equipment to make sure they're as accurate as possible. From the experimental design point of view, an important consideration is the choice of experimental units. We make sure that the experimental units we use are as homogeneous as possible, so the environment for which we're conducting the experiment is as homogeneous as possible. So for example, if we have a paddock where there's a dam at one end and we apply the treatment to experimental units, a particular treatment at the dam end of the paddock and then a different treatment away from the dam, the presence of the dam at one end may actually bias our results and increase experimental error. We're getting a result not due to the treatment, due to extraneous variation. Therefore, what we do is we make sure that we divided up the paddock so that both treatments were applied to individuals near the dam and both treatments were applied to individuals away from the dam. This technique is called blocking, and we talk about that a lot across the next two topics. More often than not, our experiments will resemble something like this and can be drawn quite simply in a flowchart. We select our experimental units, so in the human case we'd select our subjects, but it could be plants, it could be horses, it could be vines in a field. in a vineyard, I should say. So we've selected our experimental units that we're going to apply our treatments to, and application and design of the treatments is the next component of our experimental design. So we've selected our experimental units, and then we have to apply some sort of treatment, some sort of explanatory variable to test an aspect of the experimental units. So in the case of a horse study, it may be, the treatment might be feed type, feed A and feed B. And then we need to measure some response, we need some data, and so that's the final part of our experiment, actually measuring the response variable. So we select our experimental units, we apply a treatment, and then we measure a response and collect some data. This is best done in controlled conditions, so where the environment is completely at our mercy, like a glass house or a laboratory, because then we can reduce as many confounding variables as possible. But field experiments are more than likely the ones that we'll be encountering a lot, and therefore we have to always keep in the back of our mind the possibility that there will be changes in the environment and all the other things I listed before which could actually add to experimental error in our measured response. So these confounding variables are unavoidable in most cases, and therefore just have to be accounted for, have to be recorded and accounted for, taken into account when deriving conclusions. So here listed are some classic ways that our feed type experiment could be biased, or confounding variables could have an influence on our measured response, our results, our data collection. For example, a classic thing that we do, and I'd probably be guilty of doing in the past myself, is dividing up the farms based on their location. So here an example is the 40 farms in the east of the district get feed A and 40 farms in the west get feed B. Here we're biasing our results according to farm location. So it might be that in the east they get more rain, so the grass that is there is more vigorous, or the animals just get more water and therefore put on a greater growth rate, whereas in the west it might be drier, and then the reverse happens. They don't respond as well to the feed because their normal food source and their water supply isn't as good. Another classic way is that the first 40 farms that agree to take part in the experiment get the first feed, and the next 40 participants, generally the more recalcitrant ones, get feed B. Therefore, our experiment is now confounded due to the readiness to take part. So those first 40 farmers may be the most enthusiastic ones, they may be the most careful around the farm, so their animals may be treated better to start with, and they may have a greater growth rate because of that. So the best way to assign treatments to our experimental units is completely randomly, the R word. And everything in experiments hinges on randomness some way. If you're not random in the way that you allocate treatments to experimental units, or choose your experimental units, and then your results are more than likely to be biased in some way or form. Often bias, or the effect of confounding variables, may not be entirely obvious to you. May just be this underlying bias which as I say isn't obvious. And it's not till generally a lot later, when you've come to terms better with your experiment, you may have learnt some more about your experimental units, that all of a sudden you discover that you have compromised your results. One of the most important aspects of an experiment is the presence of a control. And the controls are groups of experimental units, a set of experimental units that do not receive a particular treatment. For example, in a medical trial where you're testing a new pharmaceutical, the control group would not receive the pharmaceutical. and their ordinary response would be tested. If you don't have a control, you don't know that the response variable, the response you're measuring following the application of a treatment is due to the treatment or just due to the normal behaviour of those experimental units. A placebo is a fake treatment. In pharmaceutical trials, these are often sugar pills that are made to resemble the actual pharmaceutical. These are given to make sure that the experimental units, say the humans, don't respond to say a pharmaceutical just because they know they've taken the pharmaceutical. So in some cases it's been shown that the actual thought of having the pharmaceutical rather than just taking the pharmaceutical can actually have a positive effect on patients. Therefore, in these trials, to prevent that from corrupting the results, from confounding the results, all participants are given what they think is the pharmaceutical. In the case of the placebos, they're given a sugar pill that resembles the pharmaceutical itself. This is the placebo, a fake treatment. A double blind is an extension of the placebo where even the experimenter giving the experimental unit the placebo doesn't know that that particular treatment is the placebo. And that's to make sure that the experimenter even subconsciously doesn't alter their manner when they're giving a patient the fake treatment compared to the real one. So here's just an example of what I said before in a much more confusing manner, is that in a particular report they found 40% of patients when treated with a placebo actually felt a recovery in their back pain. So they thought they were receiving a pharmaceutical to help them with their back pain, they were actually receiving a sugar pill, but 40% of these people still reported improved symptoms of their back pain in response. This is called the placebo effect.